This is Dr. Holt. This video is on the motion along a curved path. Here I have an object of, let's say, mass m. It's traveling along an arc here. We'll call this m here. Has a velocity here of v, and here it has a velocity of v. The magnitude now is going to be the same regarding these velocities. However, since the direction is changing, that's telling you that an acceleration must be taking place, because we know the acceleration vector is always going to equal to the final velocity vector minus initial velocity vector divided by some time, or delta t. In this example, I took this as being my VF, and I'll make this my VF here. I've lengthened it, doubled it, just so you can see it better. This would be VI, but I'm subtracting, so I'm changing the direction of it. And what this gives you, and let me write these as vectors too. Actually, I should do it all these. What that gives you is this delta V here. So the acceleration vector is going to be nothing more than the change in velocity over change in time. So if I take this change here and divide it by time, I get the average acceleration as I travel around this arc. Now, one thing to note here is, since we're doing average would be about approximately in the middle of that arc. Notice one thing, it always points back to the center. So your acceleration, when you go around an arc, will always point back to the center of the arc. And that's very important. Now, the thing to note is, I've seen a lot of students think that there's just some magical force appears because you're going around an arc. That's not the case. If you're going around an arc, there must be some force being applied. It could be through friction, it could be through string, it could be through some gravitational field that's creating a force as you go around an arc that's forcing this object to go around the circumference. The equation to find centripetal acceleration is going to be the velocity squared divided by the radius. That'll get your centripetal acceleration. Again, it's always going to be perpendicular to the path of the motion. So as we look back into here, again, this as I go around an arc, grab my pen, this right here will be a right angle to the tangent. See here, this will be a right angle here to the tangent. See here, it always goes back toward the center. And as mentioned here, it always points toward the center of a circle. Example, I have an object traveling 20 meters a second at an arc that has a radius of 60 meters. What is your centripetal acceleration? So the centripetal acceleration would equal to the velocity, which would be 20 meters per second squared. We will square that. We divide that by 60. And that's 60 meters. I'll do that real quick. So I take 20 squared. Oops, hang on a second, messed it up. Okay, in this example, motion along a curved path, I have an object traveling 20 meters per second along an arc that has a radius of, say, 60 meters. So the radius here out to here is going to be 60 meters. What is your centripetal acceleration? We go by definition. The centripetal acceleration, which is a vector quantity, is equal to my velocity squared, which will be 20 meters per second. We will square that. We will divide it by my radius, which in this case is 60 meters. Now notice your units here, just to do the units, that would give you mass meters squared over seconds squared divided by meters, and obviously that's going to give you meters per second squared, which is an acceleration quantity. We'll run that number, 20 squared divided by 60. That gives me acceleration at 6.67 meters per second squared. And again, that's going right back to the center circle. It always goes in. As far as the net force causing the acceleration, if this is a mass and you want to find out what the net force required, all you're going to do basically is doing force is equal to mass times acceleration. In this case, we're doing centripetal acceleration. So again, vector quantity here. That's where this equation comes from. So when we do that, the force is equal to the mass, and the equation for centripetal acceleration is velocity squared divided by r. And that's where this equation here comes from. So this will help you find the force net that's causing that acceleration. And again, that force can be caused by a gravitational force going back toward the center of the circle. It could be caused by a gravitational field at the center. It could be caused by some string that's tied to the object as you go around. A good example here, have a 2.5 kilogram stone attached to a string that's whirled in a horizontal circle. The radius here is going to be 50 centimeters. The string makes an angle of 30 degrees to the vertical. Find the speed of the stone. If you get a problem like that, first thing to do is draw yourself a good free body diagram. Like this. This will be my tension here. This will be mass times gravity here, so that'd be 2.5 times 9.8. Gives you a value of 24.5. Now this angle up here is going to be 30 degrees, so we could just draw a quick horizontal line here, and we could make this 6 degrees if you choose to. So if you get a problem like that, all you have to do is go back to Newton's second law, the summation of forces of mass, summation of forces in one direction. Do that better than that. Summation of forces in the x direction is equal to mass times acceleration in the x direction. And the summation of forces in the y direction is equal to mass times acceleration in the y direction. Again, I'll make these vector quantities. Okay, so if I'm going to do that, I'm going to let anything that goes this way be x, anything that goes up to be y. Scroll down. So when I do this, I will get minus t times the cosine of 60 degrees is equal to my mass times acceleration. My mass is 2.5 times my centripetal acceleration. And again, that's going to be negative because it's going back in. Alright, and then obviously when we set up our forces in the y direction, we also set that up to equal to mass times acceleration in the y direction. When I do this, I know my acceleration in the y direction is equal to 0 because the object's not going up or down. So that gives me t times the sine of 6 degrees plus 2.5, make that negative so we're going down, times 9.8 must equal to 0. Run that number and you'll get t is equal to 28.29 newtons. So now we can substitute back in to this equation right up here. We can say minus 28.29 times the cosine of 60 degrees is equal to minus 2.5 times my centripetal acceleration. However, do we not know that centripetal acceleration is equal to velocity squared divided by r? So we'll take that back out, substitute back in. And the thing is, we do know r. We go back to our picture. Our radius is 50 centimeters or 0.5 meters. Alright, so now all we have to do is solve for v. And we got minus 28.29 times the cosine of 60 times 0.50 divided by negative 2.5. Take the square root of that. That gives me a value of V, and V in this case would be 1.68 meters per second. Okay, in this example, I have a car of mass M, has a coefficient of static friction, I'll make that static of 0.40. I'm going to use these two equations. The centripetal acceleration is velocity squared divided by r. Again, that's always directed back toward the center of the arc. That'll always go this way. We'll be using this equation: force is equal to mass times velocity squared divided by r. Again, I'll make that a vector 2. Okay, we want to find out what the fastest this car can go around this curve. This is a flat curve. Just using this. If a problem like this, if you just draw yourself a free body diagram, then what you would end up getting would be, you would let the friction be the maximum, and it would go back in toward the center. Let me straighten that up a little bit. Go back toward the center. This value here would be mass times 9.8 times 0.40, and I'll move that over a little bit. And the other thing we'd have with our free body diagram, we have our mass times gravity coming down times 9.8, and we could have our normal force going back up. A force normal, which is also equal to mass times 9.8. Again, and this is where I got the frictional force, because the definition maximum frictional force is going to be the normal force times mu. So we have this value here. Now, when I sum my forces in the x and y, sum my forces in y, obviously my car is not accelerating up or down. I'm going to get 0, which makes sense because these two equal each other. If I sum my forces in the x direction, and what I'm going to do is anything goes this way, I'm going to let be positive, just so I don't have to fight the signs. Then I could say this, mass times 9.8 times 0.40 is equal to my mass times my centripetal acceleration. Use this equation here. Mass times velocity squared divided by r. Now come in, I'm going to give this a radius, and let's make that 50 meters. Okay, we'll take out this, we'll make that into 50. And notice what happens here, mass cancels out. Mass is totally irrelevant to this problem. Scroll down. Now our equation to solve for velocity, a velocity is going to equal to the square root of 9.8 times 0.40 times 50. We'll run that real quick. Take the square root of that, and that gives me 14 meters a second. So that would be the fastest that car could go around that curve, a 50-meter curve, where the coefficient of friction is 0.40. In this problem, I have a civil engineer is asked to design a curved section of a roadway that meets the following conditions. With ice on the road, when the coefficient of static friction between the road and rubber is 0.12, a car at rest must not slide into the ditch, and a car traveling less than 70 kilometers per hour must not skid to the outside of the curb. The acceleration of gravity is 9.81 meters per second, obviously. And what angle should the road be banked? Alright, to do this problem, first thing to do is to look at the car that has no velocity at all, just sitting on the incline. And what I did here is I took this, and I said this is just the getting ready to set up the free body diagram of the car. This vector would be mass times 9.8. I let this be theta in here. This would equal to mass times 9.81 times the cosine of theta. This would be mass times 9.81 times the sine of theta. Okay, then I drew my free body diagram. I'd have mass times 9.8 cosine of theta coming down, which I got right here. Mass times 9.8 times the sine of theta going this way. I have friction going back up this way, which would be the normal force, which would also be equal to mass times 9.81 times the cosine of theta. So this would be normal force times mu. All you do here is I set up the forces, summed them up, and let this direction be x. I'd let anything that went this way be negative, and went ahead and summed those up. And what you end up getting is the masses all cancel out, and you just get the cosine of theta times 0.12 is equal to sine of theta. Move the cosine to the other side, take the inverse tangent, and you find out 6.84. So if the angle was greater than 6.84, this car is, when just sitting here, is going to slide down the incline. Alright, now let's look at this one here, the second part, when the car actually has a velocity. When I do that, as noted, acceleration is present. Okay, to get maximum acceleration, your frictional force is going to reverse itself and going to be pointing back down. So I set this up as the maximum friction, which would be the normal force times mu of 0.12. Force normal here. I set this angle here is my theta, and again that's going to be 6.84 here. I summed all the forces in the x direction. I'll again let anything go down to be negative, or sorry, anything goes horizontal this way to be negative. When I did that, I set that equal to mass times velocity squared times r. Again, I should have made that negative here too. Let's do that real quick. Alright, and then what I did, I summed my forces my y direction, and I set the friction equal to the normal times mu. I got my normal force is 10.0125 meters. I put that back into my equation here. And let me just change this to, I need to cancel this out too. What I did here, actually, I can make this negative here because it's going back in the other way. So when I did that, I ended up just working through the equation, changed my velocity to 19.44 meters per second, and then solved my R value here. And my R value is going to give me 158.33 meters. Again, the secret to this problem, or the strategy of this problem, is just to make sure that you reverse the friction. You let the friction come down the incline, because as the car is moving around this at maximum velocity, it's in relationship to this point, it's as if it's trying to move back up away from this as it goes around the circle, around the arc. So that's why friction is going to go down. And again, that gives you just a value of the radius of 158.33.